Hello, welcome to another problem session. So today we have this interesting problem, and we could try to answer one at a time to check each one of them. But there's a common thread in the problem, you know. So when you read up there, you find that there's a setup that's very common when you're asking Faraday law problems. So this would be induced EMF, Faraday, electricity, magnetism section. I know most students really well prepare for these kind of questions. It can only say you can use some time-saving things, to make your life easier, faster, things like that. But I'm going to do something so that it just answers all of these questions on the fly. Okay. So, and also include some conceptual things along the way. So here is something, maybe this loop of wire just going at constant velocity, just the right side of the loop is here. So right side of the loop is just here, and this is the loop. Now it's going to enter, and this is conducting loop, importance conducting loop. And in a region where the magnetic field is constant, it just B0 K hat, this is the K hat direction. Okay. So this is the situation at t equal to 0, and then as it enters, these are the various things that can happen. They've been very nice that they define this combination of things. L is this length of this, and this just this is square, this L is that way too. This doesn't have to be L. For some of the problems here, there has to be L. You can just say whatever, you don't need, but it is a square loop. So this is L, Rm, and this is y-axis this way, so the velocity is all given in appropriate units. I don't know why they give you meter per second here, just should have said just appropriate units. Okay. Now the question is, if this speed is this value, will this stop before this loop reaches L here? The front of the loop reaches over there. So that's if the speed was this, it will enter, and of course it's gonna induce EMF, induced current. From that is going to have a force on it. So if you look at some arbitrary time, say sometime t, maybe this marker is y of t, and is going with a v of y of t this way. At this point, the rate at which magnetic flux is changing through the entire loop will determine what the EMF is. So right now flux is increasing, so you can use right hand rule, and so if flux increasing, then you expect current to flow this way, so that the East magnetic field is B induced is that way in the loop region. So you expect current this way and current this way. This is going to time dependent current this way. And then on that current is going to be this part will feel the magnetic field, right? This current is that way, then the force will be on this. There will be a force in that direction, magnetic force, and on this one magnetic force will be that way, and in that side magnetic force will be that way, and they will cancel each other. So the only y component, this is the y direction, so you can say Fy is going to be minus whatever the induced current is times the length of the wire, this part, which is that part doesn't matter because those forces cancel out. So this is going to be IL and B. So we need to figure out what the I will be at this instant. So this is at arbitrary instant t, we write the formula of equation of motion. So this is the force, and then I of t will simply be, I already taken the direction into account, so I don't need to worry about minus sign here. So we'll just use d phi b dt, and b is perpendicular to the loop area. So we'll just say b0, and the loop area will be the area where the b is not 0, and this part of the b is 0, so flux will be this constant comes out, dt, and the area of the loop is y, this is y, and this is L. So this just simply B0L and 1 over the, I forgot, 1 over the resistance of the loop, so divide the resistance, dy dt, and we can write that as v sub y. So this is v sub y. So now we put this v sub y. So put this in there, and this is b0. So b0 and L times b0 L equals minus b0 square L square over resistance Vy. Okay, let's use this. So m times k. So this is minus m times k Vy. Okay, the mass of this ring is m, and so the y equation, the m dvy dt, this acceleration will be minus mk vy. Of course, the m's are common, that's what they gave you, so it becomes very simple, and we need to just integrate this out to answer for different values of v0. Okay, so rather than answer each one of them independently, just get one answer. So this will be vyt will be this is very easy to integrate, right? You know how you do it, right? You can, let me write the answer first. Vy0 minus kt, that's going to be the answer. And this is simply v0 e to the minus kt. Okay, how did this so quickly? Well, let me show you over here. So dvy dt equals to minus k vy. So it just separates. You bring here and bring over there. So this just a dvy vy minus k dt, and you integrate, and so that just v0 vy of t, vy of 0 to t. So that left side is a log vy t over vy 0, because this will be minus that, and you can write log like that, minus kt minus 0. So this is just a vy t over v0 vy 0 equals to e to the minus kt, and that's what the answer is. Okay, so if I want to get where it will be at what time, you can just write down y of t will be minus y of 0, which is 0. The front part was right here at the y equal to 0. Vy t, you just have to integrate this guy from 0 to t, and you can see it's going to be minus v0 over k is minus kt 0 to t. 0 will k times t, 0 will be 1, and this will be that same thing. So it's bringing minus up front, v0 over k, 1 minus kt. So that for the y. And one of these says, oh, well, the loop will stop before it enters completely inside the region. So one of them is like a to compare that whether it's going to enter, if this speed make all the way there or not. So let's figure out because if you can eliminate this thing, we can write that in terms of y. So you can see from here, we can just do another integration, but I would just say we've already done enough integration, and so I'll just say make it k y equal to v0 minus v0 e to the minus kt. So this part is equal to v0 minus ky. So this is actually v0 minus ky, which is t. Okay, so we have enough, and so we should be able to answer all the questions from this. Let me erase and get some more clean space, okay? Okay, so let's check one out. Check A out. Check A out, okay? So if v0 is one file, loop will, okay, so if v0 is this value, what will be the y? Will y be greater than L or less than L when this thing comes to rest? So that's how I'll read this question. So 0 is 1.5 kL minus ky. So then y is equal to 1.5 L, which is much than greater than L. Okay, so we were here. I just had to go talk to take a telephone call, but I'm here now. So this says that if you want to stop under this condition, it will go all the way to 1.5 L before it stops. So this must be wrong, because it says the loop will stop before it completely enters. This would have happened within the L it stops, but it goes way more than L. So this definitely is wrong. let's see B. When complete loop is inside the region magnetic field, the net force acting on the loop is 0. Okay, so I think I just totally which is actually we don't need to use these at all to answer this. You can see that let me write that over here. So magnetic field, now when the loop is here, it's moving, delta B times A over delta T dB dt will be 0 at this point when y equals to L. Because after that, there is no more change. The B is all constant. So B is all constant. So if it goes is here or here, it's the same value. So this should be correct. Now V0, let's try C. So this is the B. Let's try the C over here. The loop comes to rest. This is at start with this, it will come to rest at t equal to that. So we should try this. So Vy t is 0 at what time? So this is V0 minus, let's see, capital T it comes to. At t equals to this. Okay, so let me so I didn't really make any mistake here. This 2/3 is fine, 2/3. And so let me go over here. So e to the minus kt is 2/3. Then minus kt, taking a natural log on both sides, be natural log 2/3. So minus natural log 3/2. Flip it. So 1 over k natural log 3. And that's what the time will be when this loop is fully in, if it starts with this speed. So this is correct. So we have B and D as an answer. Yeah, this is a pretty interesting problem actually. And if you were going to do differently, you might say, I will start with this and solve the problem. I will start with this, solve the problem. I will start with this and solve the problem. That's really not a very good strategy. Just get this formula first, and then you just work out for various V0s. They're going to correspond to different cases. Okay, so that's it for now. I will make some videos tomorrow. Okay, bye now.